Hello everyone, welcome to another CNCM lecture. My name is Noah Scheinbaum. This week's topic is on something very important in competitive math, specifically in Olympiad math and proofs. It's the Pigeonhole Principle, but today we will also be looking at it from a computational perspective as well. But before we get started, if you're new here, please like and subscribe to the channel. As of right now, we have 513 subscribers, which is a lot, and we appreciate every single one of you. But as of right now, we are trying to get monetized so that we are able to provide more prizes for competitions, provide prizes for server interactions such as the CNCM riddle challenge that we had a couple of months ago. So if we can get to monetization, and considering how big and active our community is, I believe we can, it would be amazing. So thank you so much to each and every one of you. If you're new here, please like and subscribe. Okay. Sorry for the long intro. So what is Pigeonhole Principle? It's a theorem that states if some number objects are put into a smaller number of containers, at least one container will have more than one object. Now, I know what you're thinking. This might seem fairly trivial. After all, you're not going to be able to fit 10 basketballs into 9 holes without putting at least 2 basketballs in one hole. But it can help us figure out some less trivial things. For example, if 367 distinct people watch this video, we can be 100% certain that at least 2 viewers have the same birthday, as there are only 366 potential options for a birthday. And then if 23 people watch this video, there's a 50% chance that 2 of you have the same birthday. That is completely unrelated, but that's a video called The Birthday Paradox by Vsauce that I recommend you check out. It's very good. Okay. But let's go over a problem with a slightly more complicated example. Okay, so this is our warm-up problem. Prove that if you pick 51 distinct integers from 1 to 100 inclusive, you'll always have a pair that adds up to 101. Alright, so if you imagine 50 boxes, each labeled with a pair of numbers that adds to 101, one box that says 1 and 100, one box that says 2 and 99, one box that says 3 and 98, until you get to the final box, which says 50 and 51. Okay, so now it's just a case of Pigeonhole Principle, right? Now you have 51 objects to fit into 50 boxes. You can't do that unless you put more than one object in at least one box. So one of these boxes, at least one of these boxes, are going to have both of their numbers filled, which means that one of those boxes has both of their numbers in it. Both of those numbers add to 101. We can state that a pair of numbers among the original 51 chosen will always add to 101. Okay, so that was a fairly simple problem, but it may not be super easy at first to recognize that you could use Pigeonhole Principle on these problems. They show up in many levels in competitive math, but it's typically more prevalent around Olympiad level and proof problems. And as with the last problem, it's not immediately obvious that Pigeonhole Principle can be used when solving a problem. However, once you find that it can be used and you find, like, what are the pigeons here, what are the holes here, what are the objects, what are the containers, right? The problem becomes much easier. Take, for example, this problem from the 2006 AMC 10A, problem 20. Okay, so 6 distinct positive integers are randomly chosen between 1 and 2006 inclusive. What is the probability that some pair of these integers has a difference that is a multiple of 5? Okay, so imagine 5 boxes labeled 0 modulo 5, 1 modulo 5, 2 modulo 5, 3 modulo 5, and 4 modulo 5. Mod 5, as you may have learned from our modular arithmetic lecture, or if you just had prior knowledge on this, to say that something is something mod 5 or something mod 7, that's just, or something mod 3029, it's just the remainder that that number has when divided by this number right here. So something 1 mod 5 has a remainder of 1 when divided by 5. Okay, since we are choosing 6 numbers to fit into 5 boxes, by Pigeonhole theorem, at least one of these boxes will contain more than one number. We know that for a fact that at least 2 numbers will have the same remainder when divided by 5. Again, this is just definition of this modulo notation. Using modular arithmetic rules, subtracting 2 numbers with the same remainder when divided by 5 results in a multiple of 5. If you don't know why that is, I absolutely recommend you check out our modular arithmetic lecture. I thought it was pretty good. Okay, Since we now know that among the 6 numbers chosen, 2 will have the same remainder when divided by 5, and subtracting 2 numbers with the same remainder when divided by 5 yields a multiple of 5, we can say with certainty that a pair can always be chosen among the original 6 so that their difference will be a multiple of 5. Due to this, the probability is 1. Okay. If it's always going to happen, the probability is 100%, and that is 1. All right, next question. This is a much harder example from the USAMO number 2, but once you understand where to insert Pigeonhole Principle, the problem becomes much easier. So 5 professors are attending a lecture. I put in that it was a CNCM lecture, because if you're not attending a CNCM lecture, then there's no use attending a lecture at all. During the lecture, each of them falls asleep twice, and between each pair of professors, they are asleep at the same moment at least once. Prove that 3 of them are asleep at the same moment. Okay. For each of the 5 individual professors, there are 2 moments where they fall asleep. This makes 10 moments total, and let's define this set of moments as set A. Following similar logic, for each possible pair of professors, there's 1 moment where both of them are asleep. The total number of pairs of professors is 5 choose 2, which equals 10. So let's call this set of 10 moments set B. So set A is when the individual professors are asleep. Set B is when the pairs of professors are asleep. Perfect. Okay. We'll solve this problem by assuming that all of the elements of set B are distinct, and then by finding a contradiction we can prove otherwise. Because if all of the elements of set B are not distinct, if any of them coincide, that means that more than 1 pair of people are asleep at the same time, which means that at least 3 professors are asleep. And that is the problem statement. Prove that 3 of them are asleep at the same moment. We don't need to find the moment. There's no way to do that. We have no indication of what time is. But we can prove that 3 of them are asleep. So what we're going to do is, like I said, assume that all elements of set B are distinct, and then find a contradiction. So we should consider the earliest moment in set B. Since there are 10 moments in set B, there are 9 after this moment. During this moment, 2 professors are asleep, meaning that there are only 8 members of set A after this moment. So after this first moment in set B, there are 9 moments in set B left, but there are 8 moments in set A left. Each of the remaining 9 moments in set B must fit into the one of the 8 remaining moments in set A. Since 9 is greater than 8, by Pigeonhole Principle, it is not possible for this to happen unless 2 moments in set B occur at the same time. This means that we can state with certainty that not all elements of set B are distinct, and because of that, during at least one time during the lecture, at least 3 professors were asleep. Okay, sorry that this lecture was a little bit on the shorter side. The handout will be released on Wednesday. I was just releasing the lecture now releasing the handout on Wednesday, so you guys had to watch the video and give us YouTube views. Thank you so much for watching. Look forward to seeing you all soon. Stay safe, wash your hands, and have a great day, everyone.